Hi class, today we're going to talk about 7.1, which is a trigonometry introduction. Our objective is that I can find trigonometric ratios in a right triangle with its known side lengths. We're going to start by introducing some of the key skills we need throughout this chapter, the first of which is being able to label the sides of a right triangle. Now just as a quick side note, we know something is a right triangle when it has this box in the corner that represents the 90-degree angle. And that becomes important for the first side that we're going to label, which is called the hypotenuse, because the hypotenuse is always the side across from that right angle. I'm just going to use 3 letters to represent side lengths. So why don't you go ahead and label your hypotenuse in the other two triangles drawn. So you should have gotten this side and this side. Next, we're going to talk about the side that's called adjacent. Now, in these 3 triangles, we have an angle drawn in that's 33 degrees. One side of that angle is the hypotenuse. The adjacent side would be the other side of that given angle. So in this case, the first triangle, it would be this one. Another way that I think about it is the side leg, it's the leg touching that angle, the leg that's not the hypotenuse. Again, if I label my other triangles, I've got this one and this one are my adjacents. Last but not least, we have the opposite. Now, one common question I get is opposite of what? It's opposite of the angle that you are talking about in the triangle. And in this case, in all 3 situations, we're talking about that angle of 33. So when we say opposite, we mean across the triangle from there. Okay? So we can see how that third side ends up as opposite in all 3 cases. Now again, as I noted, all 3 of these triangles have an angle of 33 degrees, an angle of 90 degrees, which by default, if you remember from geometry, the third angle would also be equal then. However, they are different sizes, meaning their side lengths are different. If we were in a class today, I would probably have you have a ruler and measure it out. But for today's lesson, I'm just going to give you what I got when I measured the different lengths of the sides. So with a ruler, I measured this adjacent side in my first triangle, and I got 3.7 centimeters. So just get these written down for now. The opposite side in the first triangle was 2.4 centimeters, and the hypotenuse ended up being 4.4 centimeters. So again, I'm just going to give you these measurements so that we can move ahead with the lesson. In the second triangle, the opposite side was 4.1 centimeters, the hypotenuse was 7.5 centimeters, and the adjacent side was 6.3 centimeters. And finally, in our third triangle, the opposite was 1.6 centimeters, the hypotenuse was 3.0 centimeters, and the adjacent was 2.5 centimeters. So a big key for this lesson and this chapter is being able to label those sides of a triangle as adjacent, opposite, and hypotenuse. And then we're going to start finding these things we call ratios. Ratios are when you divide one thing by another, and in this case, we're going to be dividing side lengths by each other. So if we look at our first triangle, you can see in our table below, we're going to look at triangle ABC, which is the first one. And we are going to take the opposite side length divided by the hypotenuse length. Okay, so I look up at my triangle, and we said that the opposite side had a length of 2.4, and the hypotenuse had a length of 4.4. So I'm going to do 2.4 divided by 4.4 on my calculator. I'm going to round, so I'm going to use a squiggly equal sign because that means about, and I got 0.545 when I divided those 2 numbers by each other. So the ratio of the opposite to hypotenuse in triangle ABC is 0.545. I'm going to continue on with that triangle, find the adjacent over hypotenuse. So the adjacent length was 3.7 over the hypotenuse length, which is 4.4. And when I calculated those, I got 0.841. And then finally, I'm going to find the third ratio, which would be the opposite side length divided by the adjacent side length. Once again, in that triangle, we said the opposite was 2.4, the adjacent was 3.7, and I get 0.649. Why don't you pause this for a couple minutes and try to do the same thing for triangle DEF and triangle GH1. When you've completed it, start it up and check your answers. So for your first ratio here, you should have gotten 0.547. For the second ratio, I got 0.840. And for my third ratio, I got 0.651. Finally, for my last triangle. Now, when I did the last triangle, my numbers didn't work out quite as nicely as I had hoped. A couple of things could have happened. I might have been a little inaccurate in my measurement, or there's a chance that when we printed or created the triangle on there, we weren't quite as accurate with our ratios and with our measurements. We'll talk about that in just a second. Okay, so now that I've completed the table, the next question says, what do we notice about these numbers? And when I say notice about these numbers, I'm going to compare the three different columns. So the answers I got in column 1, column 2, and column 3. And hopefully what you notice as you look at these columns is that these answers are very similar. So when I did opposite over hypotenuse, I got basically 0.5, 0.5, and 0.5. If I rounded just one decimal place, they actually are all equal. When I look at the second column, adjacent over hypotenuse, same thing. I get 0.8, 0.8, 0.8 if I round one decimal place. Now the third one, I would get actually 0.6, 0.7 if I round accurately because it's a 5-1, but pretty close. They're all pretty close when I look at them. And that's not a coincidence. Okay, so we can now conclude that if we do take a triangle that has a 33-degree angle and find the ratio of opposite over hypotenuse, it's about 0.5. If we do adjacent over hypotenuse, it's about 0.8. If we do opposite over adjacent, it's about 0.6. So we could use that to carry over and look at a bigger picture question. And when we look at this triangle, we're going to start by labeling the sides. Again, the side across from the right angle is the hypotenuse. Side across from the angle given, which is over here, is the opposite. And then my other side is the adjacent. Now in this case, we want to find the missing sides. Okay, so if I want to find my opposite side first, then I look back at the table. I know the hypotenuse. So if those are the two that I'm talking about, I can use the table above. And it was my original column that I used opposite over hypotenuse. And in my first column, or first row, I got 0.545. Now I probably could have just used 0.5 because that was similar to all of them, but I chose to use this one first. Now the reason we can use this is because now, since they've given me the 7.64, I can do opposite over hypotenuse is 7.64. And now I've created a little mini equation that I need to solve for opposite. Well, since I'm dividing by something, I would multiply by that 7.64 to get it to the other side. And I type that into my calculator. So I got that the opposite side is about 4.2. Why don't you pause it and see if you can use this same idea to now find the adjacent. And as you're finding the adjacent, use the adjacent and hypotenuse. Technically, we know the opposite as well, but we calculated the opposite based on some rounding that we used above in the table. So we're always going to use the one that they gave us. So now that you've paused it and tried it on your own, here's what I would have done. I'm going to use the adjacent over hypotenuse ratio from the middle column. And when we did that over and over, we got it to be about 0.84. So in this case, I only rounded to 2 decimal places. I'm not sure why it wasn't consistent. And now I'm trying to find the adjacent. I still know that the hypotenuse is 7.64, so I can set that equal to 0.084. Again, I would multiply both sides by 7.64, and I get that adjacent is about 6.4 in this case. Now this problem was actually more of an introduction to section 7.2. Our problems for tonight in 7.1 won't actually be this complex, but we do this to show you the importance of these ratios. And as we flip to the next side of our worksheet, we can see that these 3 trig ratios are not a coincidence. It's not just for 33-degree angles, but they are actually our 3 big trig ratios for all angles. Okay, now when we're talking about angles, we'll oftentimes use Greek letters, theta, beta, those types of things. They always represent angles. That's going to be key. All right. So sine of theta is actually what we're going to say is the opposite over hypotenuse. Cosine of theta is the adjacent over hypotenuse. And tangent is opposite over adjacent. We do have this acronym, Sohcahtoa, that I always like to write down at the top of my paper. I remember that the first letter represents the trig function, so sine of theta, equals, and then the OH goes in order, top of fraction over bottom of fraction. Okay, so O over H. The C stands for cosine. I need to know that means cosine theta equals A over H. And finally, TOA would be tangent theta equals opposite over adjacent. The types of problems we need to be able to solve are like 4, 5, 6. Really, it's saying find sine of theta. Well, what we just learned is to find sine of theta, to find that ratio, it's O over H. So given a triangle, I need to be able to find O over H. Well, in this case, theta is the angle I care about. So I'm going to label my sides. 4 is the opposite. The side across from the right angle is always the hypotenuse, and therefore the 3 is the adjacent. So when I substitute in O divided by H, I would have 4 over 5, and as a decimal, that's 0.8. Cosine of theta, I would have A over H, which in this case, adjacent is 3, over 5 is the hypotenuse, so that gives me 0.6. And finally, for tangent of theta, I know it's O over A from Sohcahtoa, opposite was 4, adjacent was 3, so I get 1.3. Last but not least, we do have to account for the fact that sometimes within one triangle, they'll give me 2 different angles. In this case, questions 7, 8, and 9 are asking about theta, whereas questions 10, 11, and 12 are referring to beta. In this case, I actually have to label my triangle twice. So for 7, 8, 9, from theta across, this is the opposite. The hypotenuse is 13. Therefore, this is the adjacent. So when I find opposite over hypotenuse here, I have 5 over 13. We can convert that to a decimal if we want. Cosine is adjacent over hypotenuse, which is 12 over 13. And tangent is opposite over adjacent, which is 5 over 12. Having said that, when I switch to the betas, I need to now relabel my triangle. The good news is hypotenuse doesn't change because it's still across from the right angle. However, if I go across from beta, what was my adjacent for theta becomes the opposite for beta. And therefore, what was the opposite becomes the adjacent. So therefore, when I find sine of beta, I still do opposite over hypotenuse. However, now my opposite is 12. So I get 12 over 13. When I find my cosine of beta, I still do adjacent over hypotenuse, but now I get 5 over 13. And finally, when I do tangent, I still do opposite over adjacent, but with from my beta, I get 12 over 5. So you can see that the hypotenuse never changes, but the adjacent and opposite have switched, and so it switches my numbers. You could go through and figure out the decimals for all of these as well, but to save time, I'll let you do that. Thank you very much, and again, your homework now would be to work on the 7.2 section, and have both 7.1 and 7.2 done by tomorrow. Thanks.